Hi there, this is video C12 and it is practice of FCP, fundamental counting principle, and permutations. Okay, so there's going to be probably for some of these questions, a couple of ways you can do them. And I think you should turn off the video, try them yourself first and see how they go. All right. I'm going to try and use permutation as much as I can because it's faster and easier. And I'm going to use the permutation button on my calculator because I can. All right, 12 films have been entered in a film festival. How many ways can gold, silver, and bronze be picked up? So I'm going to set this up as a permutation. And I can do that because we have to arrange the order matters. So if I win a bronze for my film, that's not the same as winning gold for my film. Order matters. And this is a section on permutations. How many films do we have to pick from? All right, 12. That's going to be our first number. That's our N. And how many are we actually awarding? 3. Okay. 1,320. You can also just for fun, 1, 2, 3, and 12 films can win gold. And then once one film has been given gold, there are going to be 11 films left over to be awarded the silver. And then somebody wins silver. And there's going to be 10. It's going to be left for a bronze. 12 times 11 times 10. Boom, exactly the same answer. That's what I was saying before. At this point, every single permutation question can be done as a fundamental counting principle question. So you're good. Either one is fine. Again, this is a minimum I want to see on a test. But you got to be careful if you're not showing me any work. If you punch it in wrong, there's nothing I can do. But don't just give me a final answer because I may not give you full marks. And if that's wrong, then the whole question's wrong. I can't even give you partial marks. Okay, 5 of the films will be chosen at the awards gala. So we're still going to use our permutation. There was 12 films to start with. How many films were we arranging? You betcha. 5. $95. There. See, permutations are your friend. How many 5 other permutations of the word decagon are there? Okay, so I'm going to permute. I need to know how many letters I have to choose from. So 1, 2, 3, 4, 5, 6, 7. There's 7. And I need to arrange. I have to deal with 5 of them. 25, 20. Again, you could do 1, 2, 3, 4, 5, and 7, 6, 5, 4, 3, and away you go. Whatever works for you. All right. How many sets of signals can be made using at least 3 flags if there are 5 flags to choose from? There is a magic word, a pay attention word, something in there. What is the phrase that says, this question isn't as simple as it looks? Did you find it? Oh, yeah. So here's the deal. If we're using at least 3 flags, then 3 flags is good. Is 4 flags good? No, I'm gonna do 4 flags because it says it. Oh, wait a minute. Got that wrong. 3 flags is good. 4. If I 4 them, well, that's at least 3. It's bigger. So 4 flags would be okay. And we could also use 5 flags. I didn't read that right. I was thinking not more than. If it said not more than 3 flags, then I would go count 3, 2, 1. But it says at least. It's at least. So 3 flags is good, 4 flags is good, 5 flags is good. And those are going to be mutually exclusives. Okay, those are going to be different cases because you can't have a flag or a signal that's 3 flags and 4 flags at the same time. They can't. It just doesn't exist. So my first one is going to be 5 permute. We're going to use 3 flags. And then this one, I'm going to set up the math and then I'll use my calculator. It's going to be 5, and I'm going to arrange or permute or organize 4. And then I'm going to have 5 permute 5. All right. I'm going to digress for a sec. Okay, so if this at least part is making you cray, if I put up 1 flag and the rule says I have to use at least 3, that's not going to work, right? If I put up 2 flags and the boss says you got to use at least 3, is this good enough? No. If I put up 3 and it says to use at least 3, yeah, I'm good. If I put up 4 and the rule says I got to use at least 3, so I use 3 and an extra. So that one's okay. And the same thing with 5 flags. I used them all. Said use at least 3, so we're good. I don't know if part about at least confused anybody, but there you go. There's a way. Yeah. Nope, leave it alone. I'm going to do the math. So 5 permute 3 is going to give me 60. And 5 permute 4 is going to give me 120. And 5 permute 5. Try that again. Permute 5. Okay. I'm getting all twitchy. 5 permute. Did I do this wrong? 4. Nope, they're the same. Okay. Now, my total. Remember when you have different cases? You know, total them up. 120 plus 100. Whoopsies. 120 plus 60. Should be 300. There we go. Oops, sorry. Page on you. All right, a coin is tossed 8 times. How many different outcomes are there? Yeah. Have I got 8 things and I'm arranging it? Not really, right? I'm not arranging 8 coins in a row. This is one. At the top it said there's some fundamental counting principle. This is one where you can't permute. So 1, 2, 3, 4, 5, 6, 7. I'm going to toss my coin 8 times. So 8 things are going to happen, 8 decisions. How many choices do I have for each one? One of those can be heads or tails, right? So what goes in the blank? 2 times 2 times. Whoops. I'm being lazy. I'm using my exponential key, which on here shows up as That's called a caret. Looks like a little house key or a little DP key. Okay, so it's a little house. And that means 2 times 2 times 2 times 2, 8 times over. And 256. So that means I could have heads all the way through, and then a tails at the end. And I could have heads all the way and a tails there, but still heads there. There's 256 ways to arrange all that. Okay. A corporate president must select a manager and an assistant for each of 2 stores. First store has 9 employees. The second store has 7 employees. Assume that all the employees are equally capable of being a manager or an assistant manager. Okay. I'll look at this question in 2 different ways, because it's a pretty cool one. It's a combination of fundamental accounting principles and permutations. Maybe you can do it without permutations, you can do it with permutation. Whatever makes you happier. I'm going to do fundamental accounting principle because it's pretty straightforward. Okay, so manager 1, assistant manager 1. That's the first store. That's what we got to pick. And then we're going to go to our second store and we're going to go manager 2, assistant manager 2. Because those are the decisions that the president must make. So my first store has 9 employees. Goes the manager the president goes, looks at all the people, and he says, yes, this person, Bob's going to be the manager, and Bill is going to be the assistant manager. I didn't state it, but let's assume that the manager and assistant manager can't be the same person. And then he's going to go to the second store. It has 7 employees. 7 and 6. Oopsies. Wrong button. 9 times 8 times 7 times 6. 3024. Now that question had absolutely nothing to do with permutations. Because remember, any question I can use permutations on, I can also use fundamental accounting principle. A different way to think about it. Store 1, store 2. At our first store, there are 9 employees, and we're going to arrange 2. 9 permute 2. We're going to pick 2 people in order matters. And at our second store, it's going to give me 7 employees. So it's going to be 7 permute. I'm picking 2. And we're going to multiply those. So decision at our first store, decision at the second store. And I'm really hoping we get the same answer. 9 permute 2 times, I'm going to do it on my calculator, 7 permute 2. Yay! 3024. Personally, I think in that case, that one's a lot easier to understand. But it's the same thing, right? Permutations, like I said, are really good when the numbers get big. If it's just a limited number, I mean, fundamental accounting principle. It's pretty sweet. I'm looking at number 6 and I'm like, I don't know. That one really kind of freaks me out. So we're going to go way back to stuff we did at the very beginning. We're going to do a tree diagram. Because, I don't know how to make the math work. Once we get the answer, maybe we can go backwards and say, oh, well, yeah, I should have done this. All right, so hold on for a sec. One question. There we go. Don't really know what happened. Right, so here's the scoop. I'm going to do a tree diagram. So this is question 6. Here's my start. And what I'm going to do is that coin is tossed. So 2 choices. It's going to be heads, or it's going to be tails. Sorry. And then it says, if it comes up heads, it is tossed again. Then we can have heads, or we can have tails. So going this way, there's 2 possible outcomes. We have heads and heads, or we can have heads and tails. But then the question says, if it lands tails, a 6-sided dice is rolled. 1, 2, 3, 4, 5, 6. So now we can get tails in 1, 2, 3, tails in 4, 5, tails in 6. 1, 2, 3, 4, 5, 6. Okay, I don't know why I had to count that. So this and this are mutually exclusive. So this is my first case. This is when you toss heads. So there's 2 choices there, 2 arrangements. And this is where we have tails. And there's 6. There's a grand total of 8. Now, by doing it in a tree diagram, I know I have covered off every option. So I'm just going to write C. And let's put next page. And there's going to be 8. Is my answer. Yeah, no, I can't really figure out how to do that unless you do like heads, and then it would be like 1 choice. It's got to be heads, and then heads or tails, which is 2 choices. So this gives me 2 there, and then I can go tails. Tail 1, and then a dice, and there's 6. That seems really awkward, and I'd be worried about messing something up. So sometimes you have to go way back to the beginning and use your tree diagrams. Right. Almost done. How many arrangements of the numbers 1, 2, 3, 4, 5? Oh yeah, there's 5 of them. If each digit is used only once. So 5 numbers, and we're going to arrange all 5. That's 20 choices. Now, remember, I said you cannot do repeats with permutations because you're arranging theoretically actual objects. So repeats aren't allowed. So here you definitely have to use fundamental counting principle. So there's 1, 2, 3, 4, 5. And if I can repeat them, it's going to be 5 choices. And then I can use the same number again. One, 2, 3, 4, 5. Yeah. Oh, I did it off screen. All right. Whereas just for comparison purposes, this would be 1, 2, 3, 4, 5. But once I use a number, if I can't repeat it, then it's going to go 4, 3, 2, and 1. Okay, so that's why there's the big difference in the numbers. But maybe here you can see what happens with my numbers. If it's only used one, in other words, we cannot repeat it, we're going to count down. If we can repeat it, then it just stays constant at the 5. Okay, last one. 4 people get on a bus with 6 empty seats. How many different ways can they be seated? Let's see. There are 6 seats, and I'm going to organize 4 people into them. So, sorry, 6 moved 4 is 360. Or you can think 1, 2, 3, 4. There's 4 people. And when the first person gets on the bus, there are 6 empty seats that they can choose. 6 choices. So he or she sits down. And then the next person happens, and they have 5 spots left. 4, 3, 2. How about I learn how to count? Try that. 6 times, whoopsies. 6 times 5 times 4 times 3. Yes. Same answer. Which way do you want to test? I don't care. This is going to give you full marks. And this is going to give you full marks. And if you need to do the I still get 360. I probably honestly wouldn't use this if I have my permutation button on my calculator. But if I don't, and I've just got one that's got an exclamation mark on it, ta-da, you can use that. This one works like a charm. I can tell you a story. Back in the old days, kids, in the previous millennium, when I was in grade 12, God bless Mr. Willock at the Yorkton Regional High School, we didn't have fancy calculators. Okay, we did not have slates and abacuses. Not that old. But what we learned and figured out with doing these is this number at the back always told us how many blanks to draw. And this number up here told us where to start counting down from. So if you ever want to do a quick conversion between this and fundamental counting principle, this is the number of blanks. This is where you start counting from. And 6, 5, 4, 3. And because we didn't have an NPR button on the calculator. All right. There's just a little extra tip for you. Ms. Warlock, I hope you are happy in your retirement.